We'll see how we do with the cloud. So let me jump over here real quick. So welcome everyone. My name is Scott Lytle. I'm the chapter chairperson of the IEEE EMC Society here in Southeastern Michigan. And I thank you all for joining us this evening. Currently we have 28 people who joined us out of 42, and we welcome you all. If you're just getting on here, please mute your microphone so we don't interrupt our speaker. After this presentation, you're invited to stick around. We're going to put up a link and a QR code. We're going to have a quick contest with just a few questions, multiple choice questions. And the first person who can get them all right will get a first place prize courtesy of Raymond EMC. Second place will be $50. And third place will be $25. So please stick around for that. This evening's presentation is by Louis Feudy. Louis has been a product safety EMC, telecom, and belt core engineer, engineering manager, salesperson, sales manager, and corporate trainer. He has worked at Underwriters Laboratories, Intertech, TUV Rhineland, and US Technologies. Lou has also been a global and US sales channel manager selling equipment for Keytech and Thermo Fisher Scientific, as well as TestSec and Amatech. He's had a total of 39 years experience in the compliance testing industry and has authored a number of articles for Compliance Engineering and in Compliance Magazine. Lou is currently US Sales Channel Manager for Raymond EMC, the anechoic and semi-anechoic chamber, reverb chamber, and shielding enclosure manufacturer. So at this time, I'd like to turn over control back to Louis. I'm gonna see here, make host. Take it away, Louis.
Thank you, Scott. I appreciate it. First of all, I'd like to say thank you, everyone, for the opportunity to speak today. I consider it an honor and a privilege to stand in front of you, or I would normally stand in front of you, or at least to sit in front of you today and provide you with some information and the opportunity to tell you about some of the things that I've learned in the industry. For the most part, I am, as Scott said, the national sales manager for Raymond EMC. We are a manufacturer of chambers, pretty much a variety of chambers, as well as parts, materials, and so forth. You can reach me at any time if you have any questions regarding any aspects of your chambers, and I'd be happy to help you with it. With that said, I'd like to go into the presentation. Scott, if you can, just let me know that you still see my screen right now.
Yes, we can see it.
Okay, good. Thank you. So what we're going to talk about today is the design characteristics and verification requirements for chambers that test to CISPR 25 and ISO 11452-2. Excuse me. CISPR 20, the things we'll be reviewing will include the CISPR 25 scope, some key definitions, qualification of a absorber line shielded enclosure chamber, design characteristics of the chamber, chamber verification methods, which is most important. And the two methods we'll be going over will be the reference method, the reference measurement method, and the long wire measurement method. And some of the items that can have an impact on the testing or the performance of the chamber, and that if you are failing the requirements, you may be able to do some items that will allow you to pass after implementation of those changes. Let me just, there we go. So you guys can focus on the screen. So CISPR 25, as you all know, CISPR is the International Special Committee on Radio Interference. I can never speak the French, so I always try to go with the English translation. part of the International Electrotechnical Commission, or the IEC, and they draft standards for controlling electromagnetic interference for electrical and electronic devices. Two types of standards that the IEC puts out and CISPR puts out. One is what's considered a guideline standard, and that standard is used to act as a guideline for committee members who are writing standards for specific products or product categories. And obviously the other one is the product specific standard, which uses those guideline standards and to create, evaluate, and verify that a specific product or product category is compliant with a specific set of requirements. The CISPR 25 standard, excuse me, is a standard for vehicles, boats, and internal combustion engines. And what we're really concerned about with CISPR 25 is the measurement for the protection of onboard receivers. And onboard receivers can include sound and television broadcast receivers in the vehicle, land mobile radio, radio telephones, amateur citizens radio, satellite navigation or GPS, Wi-Fi, Bluetooth, any aspect that's basically wired into the vehicle harness or can be added as an aftermarket add-on to the onboard power connectors are considered to be onboard receivers, or receivers that are on board and that are protected by this standard. And again, we're trying to find the limits and methods of measurement for the protection of those onboard receivers. Now, the most recent publication of CISPR 25 is edition 4, 2016, with a corrigendum 1 that was published in 2017. Provides the test procedures and emission limits for both entire vehicles, electrical system onboard components, which is clause 5, and modules independent from the vehicle, which is clause 6, from 150 kilohertz to 2500 megahertz. And as it says here in the actual standard, it sets the limits for electromagnetic emissions from components to prevent objectionable disturbance to onboard receivers. Protect the receivers in the vehicle from components and modules in the same vehicle. Does not cover protection from RF emissions and pulse type voltage fluctuations. Those are ISO standards. However, the requirements for the CISPR 25 chambers are the same, and they can be used also for ISO testing as well. The limits recommended and subject to notification by the vehicle manufacturer. This is a standard. However, there are variations due to Nissan, Ford, GM. All the vehicle manufacturers like to add their own requirements to it as well in order to ensure that it meets their specifications as a company, but all of them follow the guidelines and the qualification of the chamber under CISPR 25. Some of the things we'll be talking about today is a shielded enclosure, which is basically a steel box grounded with a Faraday cage, which is electromagnetically separating internal and external environment. ALSC is the absorber lined shielded enclosure, which is specific to CISPR 25. Bonded is that any two pieces of metal will have a DC resistance less than 2.5 milliohms. The reference ground plane is the flat conductive surface, which is on the ground, basically, whose potential is used as a common reference. And then the validation ground plane is the elevated reference ground plane with the dimensions of 2.5 meter by 1 meter. It's used as a standard for reference measurements and for the modeling per Annex J, which is the annex that provides the guidelines and procedures for qualification of a chamber. Again, either by the reference site reference method or by the long wire test. Shielded enclosure provides an environment with ambient electronic noise, a minimum of 6 dB below the emission limits specified. So most times a shielded enclosure provides much more than that. We're looking at, from magnetic, at 55 dB at 10 kilohertz. We're looking at 100 kilohertz or 150 kilohertz normally is the starting point for CISPR 25. So we're looking at 95 dB average and 100 dB from practically 1 megahertz all the way up to 1 gig or even 18 gigahertz. From 18 to 40, I believe it drops down to 95 again. These are, for the most part, the standard shielded enclosure shielding effectiveness that we provide to our customers on a daily basis. Some of the important components of a shielded enclosure include the single leaf door, the honeycomb vents to prevent any electromagnetic noise from either entering or leaving the enclosure, but allowing for airflow. Electrical power filters, again, allowing for electrical power to come in and out, but at the same time, preventing any other aspects from going in and out of the chamber. Pipe penetrations, which are usually capped at the higher frequencies, but can act as lower frequency entrance or egress into the chamber. Bulkhead panels with connectors, which are also very, very helpful. Usually N and SMA connectors are mounted on there, as well as a large variety of other types, including LAN connectors, RS-232, RS-435, and so forth. And the lighting, which obviously has to be able to light the internal portion of the chamber without allowing for any electrical power or noise to come in. And the lighting should be quiet as well. Most of the time, you'll either find it to be a 60 watt bulb, but a direct 60 hertz lighting system, or there's a lot of LED systems that we provide that also provide noise floor that can work very well for CISPR 25 as well as mil standard 461 and DO160 chambers. Absorber line shielded enclosure is with the steel walls, there is the issue of reflected energy, and that can cause measurement errors as high as 20 dB. So absorber material is lined on the walls and ceilings. There is no absorber on the floor for vehicle tests. You can provide ferrite tile up to 25 millimeter thick to the floor for component testing if the ALSE performance or the absorber line shielded enclosure performance in this configuration meets the requirements of Annex J of CISPR 25. And there's a minimum size determined by ensuring a 1 meter separation of both vehicle and the EUT and the antenna from the nearest surface of absorber material, or the tip of the absorber. And I'll show you a illustration directly from the standard, which shows that layout. For radiated emissions, you should have a clean room. Clear out all items that may be reflective or reflection sources. The material itself, of the absorber material, performance shall be greater than or equal to 6 dB from 70 megahertz to 2500 megahertz, which is the specification for the absorber. Mil standard chambers and DO160 chambers also have a specification for absorber, and that is the only specification for qualifying a room. However, in addition to this minimum requirement of 6 dB from 70 megahertz to 2500 megahertz, CISPR 25 also requires meeting the requirements, either the reference site method test or the long wire test, as it says in the next line. So this is an example of ferrite absorber. Ferrite is the tiles that you see on the walls in the lower segment, and the absorber is usually polyurethane. Most of the time it's painted with a plastic coating to allow for waterproof and other aspects, yet not having any impact on the performance of the material, which is to absorb the electromagnetic energy, convert the heat, and run it down through the walls of the chamber. As I said earlier, you would want a minimum 1 meter distance. So what we're seeing here is a 1 meter distance between the antenna on the car itself, the car, and any aspect or tip of any absorber that lines around the chamber itself. In addition, a lot of the testing for electrical cars will require an artificial mains network, power mains. All these items are called out on the left-hand side as the key for doing your measurements in the chamber itself for an automotive chamber. And to give you an example of how large these chambers could get, I'm sure you guys have seen these in your area. This is an example of an absorber line chamber. You'll note that it has both the absorber and the ferrite behind it, which is the black area located somewhere in this area right here. And as well, the ferrite is behind the absorber cones themselves as well. And we'll find as well that the floor has no cones or ferrite on it. The antenna system is a standard 50 ohm system that you use with pretty much any emissions testing. You'll use a vertical monopole from 150 kilohertz to 30 meg, 30 to 300 is a biconical, 200 to a gig is a log periodic, and 1 gig to 2500 is a horn or a log periodic antenna that is good enough to reach that value. This is similar to any other testing you're doing with EMC with regard to the materials that you're using, and they operate on a 50 ohm system. The test table is important, and there's a number of aspects that are associated with it. It should be made of at least a 0.5 millimeter thick copper, brass, bronze, or galvanized steel on the surface of the table. The minimum size of the reference ground plane for conducted emissions is 1 meter by 0.4 meters. The minimum size of the reference ground plane for conducted emissions on a current probe method rather than the voltage method is 2.5 meters by 0.4 meters. What I focus on for the most part is the minimum width of the reference ground plane for radiated emissions is 1 meter and the minimum length is 2 meters. Or if you have a large set of equipment, it should clear underneath the entire equipment plus 200 millimeters around the edge of the equipment itself. The height of the reference ground plane is 900 millimeters above the floor, and the distance from the edge of the ground strap to the edge of the next strap. And these are the straps that ground the table to the reference ground plane, not the raised reference ground plane, but the floor or the walls, is 300 millimeters between each strap. And the maximum length to width ratio for the ground straps shall be 7:1, 7 times longer than it is wide. Bonding to the chamber ground has to be less than 2.5 milliohms, and the EUT is placed on a non-conductive or low relative permittivity material, which is basically an isolating material, 50 millimeters thick above the reference ground plane. The EUT is not grounded to the reference plane unless it's intended to simulate actual vehicle configuration, which requires grounding to the auto. Side of the EUT is located at a distance of 200 millimeters plus or minus 10 millimeters from its front edge of the reference ground plane. The test harness, which is usually run from the EUT to the front line of the, or the front edge of the table, is located between the EUT and the load simulator and includes power lines, shall not exceed 2 meters, and the test harness itself is also placed on a non-conductive low relative permittivity material at 50 plus or minus millimeters above the reference ground plane. We'll show you a couple of setups from the screen or from the standard itself in a few slides. The length of the test harness, which is parallel to the front of the reference ground plane, is at least, excuse me, I should say, shall be 1.5 meters plus or minus 75 millimeters. So you'll go from 0.75 meters to 2.5 meters, or 2.25, excuse me, meters. The long segment of the harness parallel to the front edge of the RGP is located 100 millimeters from the edge. The measurement is taken at a 1 meter distance from the long segment of the test harness, which is where you locate your antenna. The phase center of the antenna is located in line with the center of the longitudinal part of the test harness. The center of the test harness that's running along the front edge, 100 millimeters from the front edge, and or with the EUT above 1 gigahertz, below 1 gigahertz, it goes with the test harness. The monopole counterpoise is bonded to the reference ground plane on the floor, and you can add additional items or additional ground cables to that counterpoise, which is also bonded to the table if you're getting some difficulties in meeting the specification and requirements at less than 30 megahertz. And the antennas, excluding the rod antenna, is calibrated at 1 meter measuring distance. This shows you the EUT, the load simulator, which is item 3, and the test harness, which is item 2, which it runs along it. And again, this is the 1.5 meter plus or minus 75 millimeters in length that is located 100 millimeters from the front edge of the reference ground plane or the test bench. And this is what the test bench looks like. In this particular case, this test bench is uses a quick disconnect segment, which we've seen before, and which we actually provide, which works just as well as the strips themselves. However, for doing the calibration of the chamber, you only have a single strip, which goes down to the ground plane, and we'll see that when we're doing the calibration. This is the rod antenna setup. As you see, the equipment, items 1 and 3 correspond to the EUT and the load system. The 50 millimeter material that is under with the low permittivity under item 1 and under item 7 represent under the EUT and under the cable, which is again located 100 millimeters from the edge of the test table. The EUT is located 200 millimeters from the edge of the RGP. And in this case, the counterpoise is bonded to the table. In addition, you can add additional grounds on the opposite side of the antenna or the counterpoise, grounding it to the earth ground on the floor if you're having difficulties meeting the specification under 30 megahertz. This shows the biconical antenna setup. Both vertical and horizontal are shown. Again, 1 meter distance from the edge of the table. I should say 1 meter, I'm sorry, 1 meter distance from the cable or the test harness located 100 millimeters before the edge of the table. And again, it's done for both vertical and horizontal measurements. And as well, the log periodic is set up the same way, showing the same test setup. So basically what you're doing is testing from 150 kilohertz to 30 megahertz using the monopole antenna. You're using the biconical from 30 to 200, and then you're using the log periodic from 200 to 1 gig, and anything over 1 gig, you would use the horn antenna. In this case, the horn antenna over 1 gig, instead of being located in front of the cable or the center of the test harness, which is located 100 millimeters from the front edge, it is instead located 1 meter from the EUT. And this is just a general indication of what would look like with regard to the inside of a CISPR 25 chamber. You're looking at full ferrite tile on walls and ceiling, and then full absorber coverage in front of that ferrite tile, which we see here, on walls and ceiling. Now, Annex J tells you how to validate this chamber from 150 kilohertz to 1 gig. Basically, this is intended to establish repeatability of results between different chambers, just as we do with NSA testing and SVISWAR for EMC chambers. This is specific for component testing per 6.5. There's a choice of 2 methods, as I've been saying along, reference measurement method and the long wire antenna method. And both methods utilize standard size validation ground plane. Change the slide. Okay. Let's move forward. Same receive antennas are used for reference measurements and for the ALSE or the absorber line shielded enclosure verification. Transmit antenna is a small monopole. 2 slides from now, I'll actually show you what it looks like, or biconical or shortened dipole. And there's 2 steps, just as in NSA testing or as VISWAR testing, there's 2 test steps taken when doing the measurements. One, you do a reference measurement method taken in OATS or a similar chamber. So basically you're taking a reference measurement on the ground plane of an open area test site, or a absorber line shielded enclosure if it meets certain qualifications. And then you take your absorber line shielded enclosure measurement again with the normal setup for doing the testing. The deviation between the reference measurements and the ALSE measurements must be within a defined tolerance, and that's usually 90% or more. And transmission and measuring equipment are network analyzers, spectrum analyzers, or receivers that can use a tracking generator or a separate signal generator. Part of the setup of the transmitting antenna is to provide ferrites that are valued at 50 ohms at 25 megahertz and 110 ohms at 100 megahertz, and they are placed every 20 centimeters on the transmitting and receiving antenna cables. The cables are routed toward the back of the reference ground plane. Less than 30 megahertz, we use a short passive monopole in a vertical position. The height, including the drive unit, is less than 500 millimeters, or 1/2 a meter. The monopole diameter is 10 millimeters in diameter. The optional top loading disc at the top is no greater than 120 millimeters. And there's a third port on this, which we'll see in a second, which is unterminated. For greater than 30 megahertz, we use a small biconical or shortened dipole placed in the EUT harness location under normal testing, which again is 100 millimeters short of the edge of the reference ground plane. And the tip-to-tip dimensions of the biconical is less than or equal to 40 centimeters. This is the less than 30 millimeter transmit monopole. It's actually shown in the, excuse me, it's actually shown in the standard itself. And the third terminal that is unterminated is the one back here. So we connect our generator through a cable to this segment. This segment is the top portion, which goes to the antenna. And this is a segment that is unterminated. Now, when you're doing the reference measurement method, you have to worry about the transmission coefficient measurement. And what that basically is the difference between the conducted measurement that you take and a radiated emissions measurement that you take using the antennas. So normal received antennas are used in the emissions measurements, the same that you normally use when doing your emissions testing are also the ones that you use to qualify the chamber. The transmitter power is measured. You drop it 10 dB and measure again to confirm that you're not overloading your spectrum analyzer or any other aspect in your measurement system. The measurement procedure is similar to, as I've been saying, a shielded, a semi-anechoic chamber normalized site attenuation method. You take your direct conducted measurement by connecting the transmit and receive antenna cables. Then the measurement is made again with the transmit and receive antennas, and the transmission coefficient is equal to the measurement made with receive and transmit antenna minus the conducted measurement that you took. A frequency step size is the same used for both ALSE and for reference measurements. And that's 481 frequencies used, 150 from 250 kilohertz to almost 30 meg, 170 frequencies from 30 megahertz to 199 megahertz in 1 megahertz step size, and 161 frequencies from 200 megahertz to 1 gigahertz in 5 megahertz step size. The initial noise floor measurement is taken with the transmit antenna disconnected, and all subsequent CT measurements must be made at least 10 dB above the noise floor measurement. Now, as I've said earlier, what normally happens is that you do the reference measurement test method on, for example, the ground plane of an open area test site, taking your measurements, and then you compare them to the measurements of the test setup in the chamber. However, the standard does allow you to use the ground plane or the floor of a shielded room as long as you take 3 coefficient measurements with each antenna moved at least 1/3 of a meter from any other measurement position. So I'm going to jump ahead for a second and show that here's our receiving antenna, here's our transmitting antenna. It's taken a 1 meter distance, and you move each antenna 1/3 of a meter from its original location and move this antenna 1/3 of a meter from its original location. And if each time you take a measurement, the difference of the 3 measurements is less than 2 dB, then you can use that as a reference measurement or that ground plane in that chamber. If it does not, or if it is not less than 2 dB difference between taking those 3 measurements, or I should say 6 measurements, where you're moving it again 1/3 of a meter on each antenna, if it's greater than 2 dB, then that site cannot be used. And then you have to either use a qualified ALSE site already or an OATS, open area test site, to take your reference measurements for less than 30 megahertz. Now, the reference measurements for greater than 30 megahertz are conducted on the reference test site, which is again an OATS or weather protected OATS or a SAC, which is compliant with CISPR 16-1-4. The elevated validation reference ground plane is required when doing testing from 30 megahertz to 1 gig, which is a 2.5 by 1 meter table. And it is not grounded the same as for ALSE and EUT testing. For doing the reference testing, it has only a single ground strap to the ground plane floor. That single strap is 100 millimeters wide and has a 2.5 milliohm resistance. And it's centered on the rear length of the validation reference ground plane. So looking at it from above, we see the reference ground plane sitting, which is our test bench for the most part. And it is grounded by a single bonding strap in the back. And we locate our antennas 100 millimeters from the front edge, as we do with our harness, testing harness. And we locate our antenna 1 meter from the edge of the table. This shows a vertical orientation of doing the same test. And this is for less than 30 megahertz. After we've done the reference measurement, which is the first measurement, which we've done on the ground plane, less than 30 megahertz, in the increments that are called out, now we're doing the qualification of the chamber with the test table in place using that ground plane. And in this case, we have the same physical layout as EUT testing. We do the monopole antenna counterpoise connected to the table, and the transmitting antenna is placed on the RGP at the center of the test harness's normal location. Again, here's our precision measurements as a reference CT for less than 30 megahertz, but with the EUT setup, which is a layout, bonding and grounding straps, et cetera, rather than a center single bonding strap. When you're doing the actual measurement greater than 30 megahertz, use a single bonding strap. When you're doing the actual testing for the qualification of the chamber, you're doing the entire strap instead, or I should say the multiple straps. Now, what you do is you take your reference measurement on the ground plane floor and you compare it to your ALSE measurement, which is the setup for the typical EUT. When you take those measurements, you subtract the reference, or I should say you subtract the ALSE measurement from the reference measurement, and that gives you your delta at less than 30 megahertz. You count those number of data points in which that delta is greater than 6 dB above or below what's allowed, or different, I should say, between the two. So in this case, we're looking at a greater or less than 6 dB measurement. We count those number of data points. For greater than 30 megahertz, we do the same thing. We do the reference measurement on the single strap bonded RGP, and then we compare it to the ALSE measurement, which is the multiple grounding straps on the table at both polarities, both vertical and horizontal. We count the number of data points that the delta for greater than 30 megahertz is either equal to plus or minus 6 dB, and we count the number of data points for horizontal that are equal to plus or minus 6 dB for greater than 30 megahertz. Once we have those numbers, we put this in this formula right here, which is the percentage of intolerance points that are measured. And that is equal to the data points of less than 30 megahertz within plus or minus 6 dB divided by the number of measurement points that we've taken, which is 481. That's the increments I called out earlier between 150 kilohertz and 30 and I think it was 200 and 200 and a gig. We multiply that times 100. We take again the vertical and the horizontal, and we do the same thing. We take the number of data points within plus or minus 6 dB, and we divide it by 481, and then multiply that times 100. And that gives us a percentage point. And then we find the minimum data points for the two data sets greater than 30 megahertz. In this case, we take the minimum of either the 30 megahertz vertical or the 30% of 30 megahertz, greater than 30 megahertz horizontal, and we take the minimum of either one of those, and that is what we use in the percentage of intolerance for greater than 30 megahertz. Then we finally calculate the total percentage of data points within the plus or minus 6 dB requirement over the entire frequency range from 150 kilohertz to 1 gig by adding the percentage of intolerance of below 30 megahertz and the percentage of intolerance above 30 megahertz. And that should be greater than 90%. It is compliant if the total intolerance numbers that you've taken is greater than or equal to 90%. So just to recap once again, we take our less than 30 megahertz measurements on the ground floor. It can be done in the chamber if we take measurements that, if they're separated by 0.3 meters in any direction, they still have a difference of less than 2 dB. If not, then we have to do those same measurements on an open area test site. For greater than 30 megahertz, we take our reference measurements using a ground plane that has a single, or a elevated ground plane, which is the table, which has a single ground that goes to the floor. Once we have those measurements, we then compare them to the less than 30 megahertz using the normal standard setup of the EUT and a monopole antenna on the test table. And then we test again for the other tests from 30 megahertz up to 1 gigahertz on the test table. And the test table differs from the calibration or original test by having multiple ground straps in the back instead of a single ground strap. Once we have all those points, we check to see if the delta between those two, any one that is less than 6 dB, we count that point. And then we divide those number of points by 481, which is a total, and then we add them all together, and those percentages should be greater when added than 90%. Somebody asked a question a while back when I did this, that can you get more than 100%? Well, if I have 90% of my data below 30 megahertz, and I have 90% of my data above 30 megahertz, adding them together, I'm going to have more than 90%. I'm going to have almost 180%. As long as it meets that specification of greater than 90%, when we have the total IT from 150 kilohertz to 1,000 megahertz, and they all add up to greater than 90%, then the chamber is in compliance with the requirements of the validation method. These data that you took between the reference and the ALSE measurements, which is the reference test versus the normal standard test procedure tests, cannot be used as a correction factor for emissions measurements, nor can it be used to produce an antenna factor for the receiving antenna. Those items cannot be done. The long wire test is the other method of doing the qualification of the chamber. And the long wire test is very similar in many aspects to the reference site method test. You have the same ferrites on both the transmitting and receiving antenna cables. The cable is routed again towards the back of the reference ground plane. The radiating antenna is a brass rod, which basically goes in the place of the harness, testing harness. It is 4 millimeters in diameter. It's located at a height of 50 millimeters between the ground plane and the closest point of the rod. It's held by two metallic sheet angles separated by 500 millimeters, which is basically the length of that rod. And then type N connectors are integrated into the angles as a rod support so that you can connect your cable directly to the rod, which is then going to be terminated on the other side. I'll show you a picture of this in a second, but basically the rod location is again 100 millimeters from the ground reference edge, then at the center of the cabling harness used for EUT testing. So we're basically putting this wire where we're going to be measuring the wire or harness when we're doing the actual testing. And we're going to be generating noise from this wire or this rod to give us data that will then be able to allow us to qualify the chamber, because again, that's how we're going to be taking our measurements later with the harness located in the same location. The metallic sheet angles that hold the rod are bonded to the higher or the table by screws or plastic clamps with a DC resistance less than 2.5 milliohms. The load end of the radiator is terminated with a 50 ohm RF load. through the type N connector, which is holding the rod in the connector. The RF feed end of the radiator is connected to 10 dB 50 ohm attenuator through the type N connector mounted in the other metallic sheet angle. And I'll show you this in a second on the next few slides. And the RF feed cable connects the RF source to a 10 dB 50 ohm attenuator. So here's our angle irons. And basically here's the end connector in which the rod is inserted into the center portion of the end connector, rather than having a wire there, the internal wire of the coax. Instead, you're gonna have a hole that's gonna allow you to make the connection to the internal wire when you make the connection to the cable. Once that's done, you put a 50 ohm load on one side, a 10 dB attenuator on the other side, and then you connect that to your generator. These brackets are separated by 500 millimeters. This is the rod that is 4 millimeters wide. I jumped it for a second. Well, we can see this either, but, and it's located at a height of 50 millimeters above the ground plane, which is at the top of the table. And that is located 100 millimeters from the front edge of the reference ground plane or the table itself. And this shows the actual value or the actual existence of the chain of the long wire and its location 100 millimeters from the edge of the table. This is obviously for doing the less than 30 megahertz test, and that we've connected the ground plane on the antenna, the rod antenna, to the ground plane on the top of the table. One of the reasons why the 10 dB attenuator is placed on the rod as well is because the voltage sight wave, the VISWAR, when measured from 4 radiation sources in the actual standard, showed a variation of peaks without the 10 dB attenuator. With the 10 dB attenuator, there is a leveling across the board, or across the entire length, from 0 megahertz to 1 gig. When you're doing the long wire test, you use your normal receive antennas again, just as you used in your emissions measurement. You again drop your power by 10 dB to ensure that there is no overload condition in either the spectrum analyzer or the receiver or any portion of the measurement system. It's the same physical layout, again, RGP size and bonding, absorber, as the EUT testing, which is multiple grounds going off the back. The monopole antenna counterpoise, which I mentioned earlier, is connected to the table, and the transmitting antenna is placed on the RGP at the center of the test harness's normal location, 100 millimeters from the edge. And this is our setup. Long wire in place of the harness, and you can see it's very, very similar to the EUT test setup, including the multiple grounds at the back of the table, as you can see. We use the same frequency step size as the reference method, 481 points. We use the same direct conducted measurement taken by connecting the transmit and receive antenna cables together. And then we take the measurement again with the transmit and receive antenna, in this case, the long wire and the receive antenna. And the signal generated amplitude is actually set to a specific value of 1 volt RMS for both the conducted measurement and the antenna measurement. And the equivalent field strength is equal to the equation of 120 dB in microvolts plus the antenna measurement minus the conducted measurement plus the antenna factor of the antenna that you're using in dB at 1 meter. Long wire antenna measurement procedure then allows for above 30 megahertz. The measurement is performed for both horizontal and vertical position, and equivalent field strength again is calculated. And again, for each frequency, we take the equivalent field strength. Max is derived as the maximum of either the horizontal or the vertical for each frequency. So you check the horizontal, you check the vertical, whichever is the maximum value, that's the value you use. And then there is a table, J1, which lists all the frequencies and the equivalent field strength in dB microvolts per meter for the calculations. You're actually comparing the data that you're taking to the data in the standard. Then for each frequency, the delta of the long wire method is equal to the equivalent in max, and the reference, you subtract the reference from the value that you measured, and that gives you a delta in dB, where again, EEQ max is the maximum field measured at a particular frequency from both horizontal and vertical positions, which we did earlier, where we took the maximum of either the horizontal or the vertical at each frequency. And then we subtract the modeled reference field, which is shown in table J1 at the same frequency as EEQ max. So basically, they're giving you an idealized value for each frequency, both horizontal and vertical above 30 megahertz. And you measure and you compare what you measure to what the reference value is, and that gives you your delta long wire method. Once you have your delta long wire, you again take the total percentage of data points within plus or minus 6 dB, calculated over the entire frequency range. So we take the data points from 150 kilohertz to 1,000 megahertz with a delta long wire method, which we subtracted the reference value minus the measured value, is within plus or minus 6 dB, divided by the 481 points, multiplied times 100, and we get a percentage. And once again, that percentage should be greater than 90%. 90% of the data should be within plus or minus 6 dB. And again, those data points that you take cannot be used as a correction factor for the emissions, and it also cannot be used to produce an antenna factor for the receiving antenna. It is strictly to qualify the chamber to see if it meets the specifications or not. Some things that can influence the parameters of the chamber validation test is the reference ground plane. It could be the bonding straps, either the number, the size, or the horizontal versus vertical, and the absorber performance. Now, in this case, we see that the influence of parameters, the influence level changes per frequency for the ground plane size, the absorber performances, and the ground plane connection. Each influence can vary. So we can see a wide variety, up to 20 dB for the ground plane connection influence. It will also be up to 20 and then going lower as we go higher in frequency. And with the ground plane size, there's not as significant an influence level in dB as we do find for the ground plane connection and for the absorber performances. Some of the modifications that you can do should help improve the AOSD performance. Between 10 megahertz and 30 megahertz, most important parameters are, again, the ground plane connections and the absorber performance. So you check your ground plane connections. You make sure that they are spaced properly. You make sure that the values of 7:1 on each ground strip is followed. In some cases, less than 30 megahertz, you may also see resonances. And in order to block those resonances, you can apply foam block absorber between the bottom of the receive antenna and the floor. And again, bond the counterpoise of the receive antenna with additional ground straps. Again, with the length ratio of 7:1 to the floor on the opposite side from the connection to the reference ground plane or to the connection of the table or test bench. That concludes my presentation, and I open the floor to any questions that you may have.
How often these tests have to be run?
Pardon me?
How often do these tests need to be run?
That's a good question. I don't know the answer to that. I believe that when I was working as a laboratory for NSA testing and for SVISWAR, we ran it once a year on the site, either the open area test site or in our semi-anechoic chambers. I would say that you'd probably want to run this test at least once a year to requalify the site or the room or the chamber each year. Now, I believe that you could probably get qualification from either NAVLAP or from A2LA And I believe that they would probably do it once a year as well. And they reevaluate your location every 2 years. So you'd probably see it once a year. Any other questions? Well, thank you for the opportunity to provide you with this presentation. And I will turn everything back over. Again, once again, I appreciate this, by the way. I hope to see you again next year with another presentation that I can come up with. But in the meantime, I appreciate you guys allowing me to do this tonight. And I will now turn this back over to Scott. Let me just find how to do that.
Let me try to grab it from this side.
Okay.
Did that work? Maybe.
It looks like it. I'm hitting you now, Scott, with the right, and it's not. Yeah, I'm not seeing
No.
transfer power, so you should have it now.
Well, I'm trying to do a chat here, and
Hey, Lou, so yeah, I see that Janet O'Neill asked a question. I think it was just quite recent. What about the test bench? Can you provide more info? I don't know what info she's looking for.
Sure. A lot of people have asked me both for this and for DO-160 and Mill Standard about the test bench. And the only specification that's given is not the materials that's used for the construction of the bench, but the ground plane above. So some are made out of wood or oak. I've seen some made out of anything that could basically act as a non-conductive material that could support as a table and that you can bond the ground plane to with glue or any other method or even screws to hold it in place before you bond the actual ground plane to the ground, either at the back of the table or the back of the chamber wall or at the chamber floor.
Yeah, I've seen all kinds of them. I've seen wood, I've seen PVC pipe, I've seen just stacks of what looks like polyurethane insulation.
Yep. As long as it's non-conductive and non-hygroscopic, so it doesn't absorb water, which acts as a reflector as well, whether the minerals in the water or anything else. If it's a non-hygroscopic material that is non-conductive and non-reflective, you can use it.
okay, any more questions for Lou? Okay, those of you that joined us late, we're going to have a, I guess you call it a contest right now. We have 3 prizes from our sponsor this evening, from Lou's company and over there at Raymond EMC. And I'm going to post in the chat window. So open up your chat window at this time. And I'm going to post a link there to a Survey Monkey. So then click on the link, go into the Survey Monkey, and there's a few questions. They're all multiple choice. So answer all the questions, put in your name and email address. And the first 3 people that get the questions correct will get prizes. So the top prize will go to the first person with all correct answers. And second place will go to the second person, and third to the third place. So, and Candace, you're gonna help with that, correct? You're on, can you pull up the Survey Monkey, Candace? And look at the stats for us? Is that possible? If not, I can dig into it.
Yeah.
Okay, so is everybody ready at this time? Does anybody need more time to get their chat window open or anything like that?
Scott, let me just say one other thing real quick.
Yeah.
They are not multiple choice.
Oh, they're not?
No, I set them up originally as just 5 questions that have some of the content that was in the presentation.
They are multiple choice.
Did you make them? Did you make them, Dennis? Okay, good, good.
Yeah,
All right.
So yeah, they are multiple choice now. And there's also a check box after you put in your name and email address if you'd like to get further information from our sponsor as well. So we'll turn over that email list to our sponsor. So at this time, I'm going to put the link into the chat window, and you guys go ahead. And I can also put up, share my screen here somehow. I'm going to share that. Can you guys see a shared screen? That's a QR code. You can, if you have a cell phone, you can get to the same survey by using this QR code. And feel free to unmute all your mics at this time if people would like to. That's fine. Thank you for the music.
I thought it appropriate.
Thank you for that music.
Because, sure. Written by Merv Griffin.
Oh, wow. There you
Fun
go.
facts, but you know, with Alex Trebek no longer being with us, there's a lot of little crazy trivia about Jeopardy that's out there now.
Can you guys see the QR code, or you still see Lou's screen? I'm not sure what you see.
I'm still seeing Lou's screen.
Okay. Oh, well, I tried.
Now we see the code.
Oh, you do?
Yep.
Would let me click two things. I don't know if that matters or not. I clicked one of the things and it jumped to the next question. It wouldn't let me click a second one.
Yeah, I'm seeing that too. We're not given an opportunity to pick the two that we'd like to, but I got the 100% anyway.
You pick
I think you should only pick one, but I don't know how Candace set it up. So,
I didn't get 100%, but I thought that was the same.
any responses? Candace, you might have to refresh and go back into the survey. Let me see if I can find my survey. I think you got to click on Analyze Results, Candace. And I don't have the answers in front of me, unfortunately. So it looks like we've got 9 responses so far. But I can't really tell past that. So Candace, if you can hear me, so go to the Analyze Results and then click on Individual Responses. And you should be able to see them, I believe, in order of that they came in. So, yeah, there's
I think there was one question too that asked if it was 200 millimeters or 20 centimeters. And it only allowed you to pick one of the answers.
Uh-oh. It's called a trick question, right?
I got that one wrong, but I think it's a technicality.
So we can't hear you, Candace, but Candace says we have 10 responses now. So we'll give, I'm assuming we have some right ones in there, but who knows? Who knows? So we do have a spread on our answers.
Where is it? How do you go back and see the Survey Monkey? You can't do it, can you?
It's in the chat window.
Okay.
You open your chat.
I mean, go back and, okay. I can't go back and see my results right now.
No, I could probably sift through them one at a time, but.
Because the centimeter and the millimeter questions, I think there's two, I think they're the same thing. Isn't 20 centimeters the same as 200 millimeters?
I think so.
Wasn't that the question, or did I get something wrong?
Yeah, there was a question about how far the DUT has to be back from the edge of the ground plane, and there was there was a 200 millimeter answer and a 20 centimeter answer.
Yeah,
Twice as many opportunities to get it right.
The diagram, I think, is all millimeters. So.
Yeah, but.
Yeah, but I know.
Right.
Well, in the event of a tie, we'll have to give it to the dimensions on the drawing, right?
Well, that means I got 100 there, not 80. Because I did this, it's still correct. Correct is correct.
That'll be up to our judge. Our judge will have to handle that. Judges, like on the Jeopardy, we have a complete panel of judges out there that you can't see.
So I got 100 because there it is. Because 20 centimeters is the same as 200 millimeters. So number 2, I got that right.
Yeah, but the plus and minus parts are different because you got 10 centimeters versus 10 millimeters.
Okay, it's still wrong. Well, I'll give it, that's true.
Oh, here comes it. Here. So, let's see here. What am I looking for? Jump screens that I didn't want it to jump. Analyze results, respondent 11. So Candace, they come in the order of the respondent number. So if you jump to respondent number 1, that's the first one. So look at respondent number 1 and then see if they got them correct. And then you can actually, with the arrow keys, you can step through. It says, actually, let me double check that. So respondent 1 was 653.19. Respondent 2 is 653.22. So yeah, so they're in order of respondent numbers, if that helps, Candace. And that's on the Analyze Results page, and you can step through with those arrow keys. We need some more Jeopardy music at this point. Jump over to my email. Okay, let me write some stuff down here. So I will help with this. Oh, it looks like it. Oh, I've got another text message here. One moment, please. Um, one second. Wait a minute. First. Oh, you have two firsts. Okay, we're almost ready. Sorry for the delay. Sorry, this is taking so long. to unmute. Okay, can you hear me now, everybody? Hello?
Yes.
Yes, we
Yes,
can hear
we
you.
can.
Great.
Yep.
So the earlier question, one of the people said was 200 centimeters and 20 centimeters versus 200 millimeters, but the tolerance was different. So that was truly a trick question. So 200 millimeters was the only correct answer on that one. So we've tabulated these, and the first place winner this evening to get them all correct, and the first person to get them in all correct was Tom Barucki, B-O-R-U-C-K-I. Tom, you there? Tom, unmute your mic if you got. Congratulations, Tom. Well, maybe he's not going to. Second place went to Dan Brazier, B-R-A-S-I-E-R. $50 gift certificate goes out to Dan.
Thank you very much.
You're welcome, Dan. And then the third place goes to Josephine Root for $25 gift certificate. Congratulations, Josephine.
Thank you. You should pass that on to the next one.
Why is that?
Because I took it twice.
Well, it depends on what order it came in, though. I mean, if the first one that came in correct, because a lot of people answered, but they weren't correct. So we just skipped to the next. You had to have 100. These are the first people in order to get 100%. Correct, Candace? Or
Yeah.
Yes, it's
Yeah.
100%.
Okay.
The first people to get 100%, yes.
Okay.
Congratulations, Tom, Dan, and Joe. I'll have the cards sent out, and I guess I'll work with Scott as to how to get them over to you guys.
Yeah.
Very good. Thank you.
Do you need mailing addresses, Lewis, or is the email address okay? You can just email them and get their information if I give you
That
their.
would be fine. Yeah, if you want to just give me their email addresses on it, and later on I can contact them to get a mailing address, and then we'll send the cards out.
All right, so we'll do that. I have all your email addresses, and I will send in those off. So thanks again, everybody, and sorry for the slowness at the end there. But again, thanks again, and we'll see you next month.
Good night, everybody. Thank you very much.
Thanks, Scott.
Good night. Thank you.
Thank you.
Good night, and thank you.
Thanks for coming.
Bye now.
Bye-bye.